Welcome back. This is video 2 of our distance formula series. In this video, we're going to do a relatively simple example of how to compute a distance. We're just trying to get our hands on trying to do the formula itself. We did a really simple example in the previous video. We're going to up the ante just a little bit and do something that's just a little bit more difficult by throwing in some signs and stuff, but we'll see that the formula actually works out just fine doing it this way. So let's give this a try. So we're going to take a couple of points here. I'm going to first start at -2, 3. So the coordinate we're going to use is 7, -9. So to draw the line between these guys, we're going to get something a little like that, about that. Now, to compute the distance here, all we have to do is plug it into that distance formula. So again, let's write that out, what we found from last time. The distance is the square root of x2 minus x1 squared plus y2 minus y1 squared. This here is going to be our x1 and our y1. This down here is going to be our x2 and our y2. All we have to do at this point is plug in x2 here for that coordinate, x1 for that guy, y2 for this guy, and y1 for this guy here. And we'll just plug it in and then we'll solve and see what we get for d. So here we get the distance is going to be equal to the square root of, well, x2 is 7. We're going to minus a -2. So make sure whenever you plug in a negative number, you do it in parentheses so that you make sure that you resolve this sign correctly. And then we'll put in a y2, which is -9. Like I said, you can put that in parentheses on its own. And then we're going to subtract doing the 3. Now that parenthesis doesn't actually do anything, but it's good practice to always substitute in using parentheses in order to avoid weird sign issues. So this will tell us that the distance is equal to, well, we have 7 plus 2, because minus -2 becomes a plus 2. So that's 7 plus 2 squared plus -9 minus 3 squared. So if we come down here, we've got our d is equal to the square root. Well, this is 9 squared, and -9 minus 3 is -12, -12 squared. So we end up with d is equal to the square root of 81 plus 144. And if we add those together, we get the square root of 225. The square root of 225 is 15. So this tells us that the distance here should be equal to 15, whatever the units are. So that's how you do it by putting it into the formula. But let's see what happens if we actually try to measure this out and see if the formula is actually capturing what it should. So we'll do this problem again, but we're going to do it on a piece of paper where we actually measure out the distances really precisely, and then we'll compute the distance not by plugging it into the formula, but just simply by measuring with a ruler how long it should be to see if the formula actually gave us the right answer. All right, so now we're going to take a look and see if we can measure this exactly and see if it works out. So we're going to do the same problem that we just did, but instead of using the formula, we're actually going to try to measure things and see if it works out. So here we'll draw our XY plane real quick. So we're going to make some marks here that are exactly 1 centimeter in length. Now the 2 points that we're interested in are -2 and 3. So we go down to -2 and up to 3. And then we're going to pick 7, which is all the way out to here, this tick mark, all the way down 9. This is our 0.7, -9. Now let's draw the line between them, which is going to be almost the entire length of this whole thing here. And then what we'll do is we'll measure and just see how long this is. So if we take a look and we try to measure this, you can see, remember, everything here is to scale. Everything's a 1 centimeter scale. So 1 in this should correspond to 1 centimeter. And sure enough, you can see that the length of this is exactly 15 centimeters from point to point. So here's that first point really big. Here's that other point really big. It's exactly 15 centimeters across. We can actually do the horizontal part if you'd like. We can make sure that we do this parallel. So we go all the way out to 7. Sure enough, that's going to have a distance of 9. And you can see that that measures 12, just as we expected. So the distance from 3 down to The distance from 3 down to -9 is a distance of 12. And across the top is a difference between 7 and -2, which is a distance of 9. And we measured this one at 15, and you can see the right angle there. So you can actually see the geometry coming out. If we do it to scale and we measure it carefully, you can see precisely what's going on without even having to do the distance formula. But we got exactly the length that we expected. So this shows that we can use algebra as well as geometry in order to make this computation. So you can see that whether we did this by a ruler and actually measured it, or if we use the formula, we got to the same answer. Now, what is the use of this? That this tells us then that this formula is actually capturing things that are real, something that we can actually measure and that we can be certain is right. That allows us to take fewer measurements and use a computation to get the measurement that we don't have to do or that might be kind of complicated to try. This is actually one of the ways that surveyors can get distances, is by using things like the Pythagorean theorem and stuff like that in order to deduce what distances have to be given certain kinds of information. And that's kind of what you're learning about here, but we'll get to a little bit more of that later. That's it for our second video on the distance formula. Join us for our next video where we'll do a more complicated example that uses the distance formula in an application. If you're interested, you can check that video out here, or you can check out this video for a more recent general interest video on our channel. If you like this video, please click that like button and subscribe to Scholar Sauce. We have lots of really great content coming and you don't want to miss out. We'll see you next time.